Our last talk for this session is by Guy Blachar, who we're talking about probabilistic laws on infinite groups. So take it away.
So thank you very much. And first, I'd like to thank the organizers for the invitation to speak here today. And as the title suggests, I'm going to speak on these probabilistic laws on groups. So first, maybe I should start with saying what is a law? Well, a law will be, for us, any equation of the form some word in a free group equals 1. So I have several variables, and I'm allowed to multiply them and add inverses, and I want this expression to equal 1. And we say that the group satisfies the law if for any substitution of elements from the group, the law equals 1. The law is satisfied. So the basic examples are probably a billion groups satisfy the law that the commutator of two elements equals 1. And if you have a group of exponent n, it satisfies that x to the n equals 1. And the nilpotent groups satisfy, these step nilpotent groups satisfy that the iterated commutators after these steps equals 1, and also solvability can be written this way. So basically, any word we can put 1, this gives us a law. So while sometimes, if a group satisfies the law, then of course we have some structure, but we can also ask how close can a given group be to satisfy a given law. So how close can a group be to being a billion, or to being nilpotent, or to being exponent n, or any law that you would. So we'll start with some, we'll discuss a bit about the finite case first. So in the finite case, this is much easier to explain or to think of how to define it. Well, the idea is that we'll just, if the law has d letters, we'll just randomize each of them uniformly and independently and ask what is the probability that it equals 1. Or basically, we just choose a random d tuple of elements of G uniformly with repetitions, of course. And then we ask what is the probability that the law is satisfied. So the commuting probability will be what is the probability that two elements chosen randomly will commute with each other. And two questions that we'll ask today are how close can a group be to satisfy a law? And so that's one question. And the other one, if this probability is big, what can we say about the group? Because, for example, if we know that the probability that two elements commute is, let's say, at least 1/10, then the group has to be in some sense close to being a billion. And these are the two questions that we'll ask. How close can it be? And if we know that it's not small, what can we say about the group? So maybe we'll begin with the commuting probability. So what is the probability two elements commute? As I said, just look at all of the pairs of elements that commute with each other over the total number of pairs. And when you think about it as first, you think that, okay, if 90% of the pairs commute, then the group has to be really close to being a billion. And if, I don't know, only 10%, then it has to be far. And maybe we can get, and maybe it should somehow show how close the group is to being a billion, and we can get as close to 1 as we want. However, perhaps the first surprising result of Gustafsson says that it can't be arbitrarily close to 1. In what sense? If this probability is larger than 5/8, then the group becomes a billion. In 5/8 is tight. The non-abelian, for example, the non-abelian groups of order 8, the hydral group and the quaternion group, both have commuting probability 5/8. There's also characterization of when this happens. And that means that if we look at all the set of possible commuting probabilities of all finite groups, I think of it as a subset of the interval 0 to 1. Well, I can get 1 by taking a billion groups, and I can get 5/8 by the examples I said, but nothing in between. So there is some kind of gap in the set of probabilities of unfinite groups. So this answers the first question that we said. For the second question, there is a theorem of Newman that says the following: if the commuting probability is larger than epsilon, then the group is what is said epsilon bounded by a billion by epsilon bounded, in the sense that there is a large subgroup H and a small normal subgroup N, such that H over N is a billion. And when I say large subgroup or large H or small n, I mean that the index of H and G and the order of n are both bounded only by functions of epsilon. So regardless of the size of the group, regardless of the number of generators that you need, just an universal expression depending only on epsilon. And this question has many other directions that you can think of. There are some directions of, can we classify those groups that have commuting probability large? For example, 5/8 we know. Those that have commuting probability larger than half, or there are several questions about the set of commuting probabilities. Which numbers can appear as a commuting probability of a finite group? And all of these are and all of this is related to understanding how abelian can a finite group be. Now, this is for the commuting probability. Regarding other laws, there are some other results. So here is a scary table, but maybe we'll go about it. We will go slowly. Well, for the commuting probability, for example, we know that there is a gap, so there is a maximal probability, and if the probability is larger than epsilon, then we said it's epsilon bounded by abelian by epsilon bounded. It turns out that also for nilpotency, this can be done, for example, by induction on the commuting case. Also, there is a gap, there is a critical probability that above which you have to equal 1. And if the group is nilpotent, you have a large case of nilpotent subgroup. And here we have this remark that the now large, and unlike the thing we had for, unlike the theorem we had of Newman, that only dependent on epsilon, now it might also depend on the rank of the group. It depends on the number of generators. This is by works of Eberhard, Chomyatsky, and Shalev proved this. Shalev proved this result, and Eberhard and Chomyatsky showed that we cannot relax that the assumption that it depends on the number of generators. So also for x squared equals 1, we have a gap which also follows from commutativity, but you can also get it in other ways. And the result of Mann shows that groups with many involutions are also close to being abelian. Now, for other groups, for other laws, for other laws, we also know that there is a gap. Sometimes it might depend on the number of generators of the group. And generally, in all of the examples that we know, there is such a critical probability, such a maximal probability per law. And if the probability is larger than epsilon, at least in these 3 cases that we know of, the group has some structure. This is still an open question for the general case on finite groups. If I have a general law, is there a critical probability for it to be satisfied? And if the probability is larger than some constant, what can we say about the group? So these are still open in the finite case. All of the examples that we know satisfy these 2 properties, but we don't have any general theory yet. So this is about the infinite case. And now let's turn to talk about this is about finite case. Let's turn to talk about infinite case. The problem with the infinite case is that unlike the finite case, we don't have a uniform distribution. We can't just take a random tuple of elements from the group because we don't have uniform distributions on infinite sets. So we have to somehow take natural choices of ways to take random elements from the group. Well, the groups that we'll be interested in are finitely generated groups. We'll take a group, we'll fix a finite symmetric generating set. We'll also assume that it contains the identity. This is just to avoid some parity issues, just to make sure that no technical issues will appear. And here's a natural idea that appeared in the work of Antolin, Martino, and Ventura, that we can take a sequence of probability measures and define the probability that the law is satisfied to be the limit of the probability that the law is satisfied when I take the elements gi by mu n. So I have this sequence of measures, and I look at the measure mu n, take d random elements from mu n, ask what is the probability that they satisfy the law, and then let n tend to infinity. And the idea is that maybe we can choose a sequence of measures that will be supported on a finite set, but eventually will cover the whole group. And we'll choose a nice sequence of measures that will give us nice properties, or because it will somehow be connected to the group or to the natural structures on it. Now, maybe 2 technical remarks. There is no a priori reason that it will not depend on M, and this limit might not exist. So we might, if we really want to be precise, we should write P of M that depends on the sequence of probability measures that we use. And also, instead of limit, we'll take a lim sup to make sure that it exists, and we'll get a number between 0 and 1 but this gives us some way to measure how close our group is to satisfy a law. We can wonder which natural choices, which choices of sequences of measures we can choose. Well, here are two options. One option that we can choose is to take a random walk. I'll briefly remind next slide about random walks, but you can take the generating set or take the Cayley graph and just start a random walk from the identity, say, and look after n steps what happens to the random walk, and then let the number of steps tend to infinity. And another natural choice is if we already look at the Cayley graph and take balls around the identities, around the identity element, and ask what is the probability that if I take a random element of length n, that it will satisfy the law, and then let this radius tend to infinity. So we'll talk about these two choices and give some results about each one of them. So let's start with random walks. Just to recall what are random walks. Well, a random walk is a sequence of random variables. Well, I start with the identity, and each time I multiply by uniform generator, uniform elements of S. Of course, independently of the previous one, this is a random walk on the Cayley graph. And because we choose S to be symmetric and generating set, then eventually Rn will cover the whole group. So we won't miss any part of the group eventually. And then we can take mu n to be the law of Rn, so the distribution that it induces in the group, and the sequence of measures will be what happens after n steps to the random walk. So if we think about commuting probability, this will be, I take two independent random walks in the group and ask what is the probability that after n steps, their values commute with each other. Now, one particular nice property of random walks is that they satisfy the so-called measuring index uniformly property, which says that if I look at the probability that a random walk is a given coset of a subgroup, this tends to 1 over the index of the subgroup, and also this is uniform on the subgroup and the representative. So in this sense, somehow gives us a nice idea that if we have a subgroup index 2, then the probability to be in this subgroup is half, or tends to half. So this is somehow, seems like a natural choice of measures, which respects the algebraic structure of the group. And the first results that we'll mention did use these sequences of measures to study the probability of satisfying the law. So before going to our work, maybe I should mention some work, the initial work regarding the commuting probability. So again, the probability that two random walks commute after n steps, first by Antolin, Martino, and Ventura, later by Tronton, and they showed the following analogs of the finite case. First, we still have a gap, and the same number actually holds. If the probability is larger than 5 over 8, the group becomes abelian. So again, the same examples hold, of course, also show that it's tight for the infinite case, but this shows that the infinite case behaves like the finite case. And also, the second part, if this probability is positive, because we are taking a lim sup of probabilities, this could tend to 0, but if this probability is positive, the group is virtually abelian, which means it contains a finite index abelian subgroup. So indeed, we see that these are two analogs of the finite case. We have a gap, we have this critical probability, and also if this probability is positive, the group is close to being abelian. There are also some refinements of this theorem in the work of Tronton. If this probability is larger than epsilon, we can also say that the group is epsilon bounded by abelian by epsilon bounded. So we also have full analogs of the finite case. So this is perhaps the first case also in the finite theory, and good motivation for the remainder. So in our work, in the joint work with Gideon Amir, Maria Gerasimova, and Gady Kozma, we considered these kind of questions for other laws. So what other laws? For example, let's talk about the law of being of order 2. What about being of order 2 in the group? Suppose that this is positive. Now, in the finite case, there was a result of Man that says that if this probability is larger than epsilon, the group is again close to being abelian. So it's epsilon bounded by abelian by epsilon bounded. We cannot expect it, both in the infinite and the finite case, to be close to being of exponent 2, because, for example, if you take a dihedral group, the dihedral groups, half of their elements are of order 2. So this probability will tend to half. However, they don't have any infinite subgroups of exponent 2. So we can't expect really to be close to exponent 2, but we can expect it to be close to a billion. And this was stated as a conjecture by Lyman and de la Salle, that these groups will become virtually a billion. And indeed, we managed to prove it. We managed to show that the conjecture holds. Any group which has many involutions, many elements of order 2, has to be virtually a billion. And you can also get some bounds. If this probability is larger than epsilon, then the index of the abelian subgroup is bounded as a function of the rank of the group, the number of generators, and epsilon. So only depends on epsilon and the probability and the number of generators of the group. So this is another result that supports the idea that, as in the finite case, we should have some structure on the group, and it also follows from here that there is a gap, and it also follows that by works of Tuanton, Martino and Ventura, and Leonas, it also follows that this probability, the commuting probability as well as this probability, doesn't depend on the generating set. In fact, if you take 2 random walks and ask what is this probability, the probability that a random walk squared will equals 1, it doesn't depend on the generating set. So this follows from this theorem along with the results. However, this were analogs to the finite case. If you go to other laws, it turns out that something doesn't continue, doesn't hold as well. This is regarding the meta-abelian law, the probability to be solvable degree 2-step solvable, and it turns out that here the picture completely changes. In what sense? In the following sense, take the Ritz product of the 5-dimensional lattice with lamps. I'll recall Ritz products in the next slide, but this is the base group, and then I put F2 valued lamps over the points of the lattice. And for any epsilon greater than 0, we have a finite symmetric generating set such that the probability that 4 random walks will satisfy this law, that their commutators will commute with each other, can be made arbitrarily close to 1. And this shows us 2 things. The first thing that it shows is that the meta-abelian law doesn't have a gap. So there is no critical probability. The probability can be arbitrarily close to 1, although not equal to 1 at any stage, but we can be really close to being meta-abelian even if we contain a free subgroup. And that's the second thing that it shows. This group contains free subgroups, non-abelian free subgroups, so it doesn't have any finite index subgroup that satisfy any law. So it doesn't have a gap and doesn't virtually satisfy any law. That shows that in the infinite case, something breaks, something doesn't hold as well. Because every lecture needs some proof, I'll try to at least give the idea of the proof for this result. And the idea is as follows. Well, first, I will recall Ritz product. The Ritz product of 2 groups is the semi-direct product of G with this infinite direct sum of H. And we should think about it as I look at G, and on each element of G, I place a lamp with values in H. Now, we have this is an illustration of the usual lamplighter. So with classical lamplighter group is a Ritz product of Z with lamps in Z mod 2. So on each element of Z, I place a lamp, which can be either turned on or off. This is the Z2 element. And then we have this little person, this little lamplighter, that can walk on Z. Now, this group is generated by 2 elements. The action of G is making the lamplighter walk. And then the lamplighter can also change the lamp at the position that it's currently at. So these are the 2 actions. It can either walk or change the lamps. And this is a finitely generated group, and this is an example for instance of a group of exponential growth which is amenable. Also several other interesting properties of its random walk we studied. But will not delve into this. And the groups that we're interested in are the same idea, but instead of using Z, we're using Z to the 5th power, so this 5-dimensional lattice, and the lamps, instead of being Z mod 2, are from a free group. Actually, we could take any non-abelian finitely generated group, but it would be easier to explain with a free group. So let's return to the theorem, and let's give the idea of the proof. So we have this Ritz product, And I want to show that I can make random walks satisfy this meta-abelian law with high probability. So I have to give a specific generating set. So we'll write A and B for the generators of the free group, and we'll fix epsilon, the third probability that we want to get. And the generating set we will take will have two parts. The first part is just the usual walk on Z5. So we'll just take the usual walk so the lamplighter can walk as he usually does. And the second part will be how to change the lamps. We can either change A lamps at the position where the lamplighter is currently at, or we can change B lamps at a faraway position. K points to the right. K is some large constant that we'll choose later, but it's really well defined. So how does it look? Well, if we take four random walks, how does the commutator of the commutators look? Well, the commutator of two random walks will look like this. Our base group, z to the 5, is abelian. So eventually it will draw some path on the lattice, but it will return to the starting point. Now, how does it change the lamps? It can either change A lamps at the path that is visiting, so you can change A lamps at the blue part, or you can change B lamps at the translation of this loop. The translation by exactly KE1 points. So this is the first commutator, and the second commutator does exactly the same. So this is also, it performs another loop, A lamps at the path that he's doing, and B lamps where he's with the translation of this loop. So these are the two commutators, and we want them to commute. And I claim that I can make sure that the probability that the blue, by choosing K large enough, I can make sure that the probability that the blue loop will not intersect the dashed red loop will be arbitrarily close to 1. And the same for the red and the dashed blue. And why does it help us? If the blue doesn't intersect the dashed red loop, then at each point the lamps will have to cancel out when you take the commutator of these two elements, of these two commutators. Because if this is a place where only the blue loop appears, then it will just cancel itself. If we have both the blue and the dashed blue, well, we don't have any interference with this, and we'll just again cancel because when we do the commutator, we'll go on the blue commutator, then the red, then we'll take the inverse of the blue and it will cancel itself. And if it is a place where we also have both blue and red, then because the red and the blue only apply A lamps, then A lamps commute with each other. And eventually, even if you didn't follow all of these cases, I can make sure that by choosing K large enough, the probability that these two commutators will commute will be arbitrarily close to 1, and therefore the group will be really close to being meta-abelian. And that's the idea of the proof. And this proof can be generalized to other examples of laws. So in many examples of commutators of two laws, where the laws don't share any common letter, in most examples we also have similar ideas. This is really something that is related to the path of the random walk. So in the remainder of the 5 minutes that I've left, I'll talk about the other choice of measures, about what happens when we take the uniform measure on the balls. So again, we have a group finitely generated, and we fix the generating set. And this time we take mu n to be the uniform measure on S to the n. So this is the ball of radius n on the Cayley graph of G with respect to S. And I want to ask, what is the probability again that the law is satisfied when I take uniform elements from this ball? And the result that we have here is the following. If we take any non-trivial law, and suppose there is a group of exponential growth that satisfies it, we only want a group of exponential growth to satisfy it, then there is a group gamma such that for any epsilon greater than 0, we can make this the probability that the law holds with respect to this sequence of measures to be, again, arbitrarily close to 1. So also in the case that we try to measure it with Wallace and Cayley graph, this is still we don't get the same analog. Here, the difference between this and the previous result is that in the previous result about the meta-abelian law, the size of the generating set remain the same. Here, we don't have it in all cases. I'll show the idea of the proof, and it will also be clear. Well, the idea is the following. We'll take, as an example, the load W equals x to the n for large n, which also will be odd for simplicity. And here the groups that you can take of exponential growth will be a Bernstein group, which is non-amenable, so it also has exponential growth. Let's fix a generating set T, and the group that we'll take is a direct product, just a direct product of G with Z mod 2, and generally the exponential growth group with some finite group that doesn't satisfy the law. That's all we need. And the generators will be either move on the exponential growth group or move in the Z mod 2 in this component. And the idea is, without getting to all of the details, that when I look at balls in the Cayley graph of gamma, then either I didn't make any step in the Z mod 2 direction, in which case I have an element of length n in G, or I made a step in the Z mod 2 direction, and then I have an element of length n-1 in G. So it is comprised of these two sets, balls of radius n-1 and radius n in the group G. But because G is of exponential growth, these sets they have a difference in their size, and if the cardinality of the t to the n is approximately gamma to the n, then we get this probability is at least gamma over gamma plus 1 in the limit, and we can change the generating set, replace t with t squared, and increase the generating set to make gamma arbitrarily large, and then this probability can be made arbitrarily close to 1. So to summarize, in the finite case, while all of the examples that we have both have a gap, and in the few cases that we know have some structure, in the infinite case there is something more delicate. And even if we take examples like random walks or uniform measures and balls, still these phenomena do not occur, at least not for any law. So there are examples where it holds, but there are also some examples where it doesn't. That's it. Thank you very much.
Let's thank the speaker. Are there any questions for the speaker?
Yeah, so what happens if you take 3-step nilpotent?
In the finite case, or
the random walk case, infinite?
So nilpotency in general will also have a gap. It will basically follow from the abelian results. So it will also have a gap, and will also be virtually d-step nilpotent. Yeah, it can imply some inductive step there.
Okay, thank you.
Are there any more questions for the speaker? Okay, on this slide, in case number 2 of this theorem, does the probability of these two arbitrary elements commuting, does that depend on the rank of the abelian subgroup, or what does this depend on, if anything?
You can get a bound by the index of the abelian subgroup, but it can be bigger than that. There are some more explicit expressions in the work of Tronton.
Thank you. Are there any more questions for the speaker? Okay, if there's no more questions, let's thank the speaker again.